Hello everyone. We are beginning section 15.2, looking at double integrals over general regions. So in this section, we are going to be integrating over not just some rectangular region R, but over a general region that we call D. That does not have to be rectangular. It doesn't have to go from constant to constant. It can go between different functions as well. You'll notice as we go through the lecture video, I have all of the notes already filled in on here. That is because this is my second attempt at making this lecture video. I went through and made the whole thing once already, and then my tablet decided it didn't want to save the video. So I've had my practice run. I'm ready to go, and we're going to go through this. So a lot of our integration and our interpretation that we saw in the previous section is going to still hold here. So like in the case where we have a function that is greater than or equal to 0, we can still interpret the double integral as volume of the solid that lies above D and under the function f of x, y. Okay, the only difference here is that, again, we're integrating over a general region D instead of just a rectangular region R. But the interpretation is still the same. So this type of integration gets typically broken down into two subtypes. So type 1 and type 2, appropriately named. So type 1 regions are going to be ones where we are integrating vertically. So you can have regions that look kind of like this one, where you have x going from a to b, and you have y going from a function g1 to a function g2, and that defines the region D in the middle here. So we have x going from a to b, y going from g1 to g2. Okay, you can also have situations where, say, we bound the function above by b, and the function is naturally bounded by an intersection point A. Okay, so we can have situations like that, or you can have a situation where the functions actually intersect at A and at B, and that sets a natural boundary for our integration. And then we're still going between a lower function and an upper function, so g1 up to g2. If we want to compute the value of this integral, we're going to set it up like we did for the rectangular region. The only difference is that now we're going to be integrating the y's, so with respect to y, between the functions g1 and g2. Okay, and then of course x is going between a and b. So again, same integration techniques, but now you're going to have functions with variables in the bounds instead of just constants up in the bounds. And like I said, when it comes to the type 1 integration, I refer to this typically as vertical integration. That's because I find that remembering type 1 versus type 2 can get kind of confusing because those are just labels that we put on it. So really it's indicating that we need to integrate vertically. So then the type 2, that's going to be our horizontal integration. So the horizontal integration, here we have a region that is defined between two functions of y. So x is defined between h1 of y and h2 of y. So that's like these down here. And then y gets bounded from c to d. Okay, so horizontal integration, something we learn typically in Calc 2, I think. So this is going to be approached the same way, but this time we're going to set up the integral with respect to x first, integrating between h1 and h2, okay, so between those two functions of y. So you're going to have functions of y in those bounds, and then integrate with respect to y between c and d. Okay. The idea here is that after you're done integrating with respect to x, you're going to have a result that has a bunch of y's in it, and then you're going to integrate that with respect to y. So then you will have a single integral with a single variable. Okay, same thing from above. And so then again, this is considered just horizontal integration. So these are our two types. So we have type 1 is vertical integration, where we're going between functions of x. Type 2 is horizontal integration, where we're going between functions of y. So let's go ahead and look at an example. So we're going to evaluate the double integral of x plus 2y over the region D, where D is the region bounded by the parabolas y equals 2x squared and y equals 1 plus x squared. Now, in order to get boundaries on this, we need to figure out where these parabolas intersect so that we can see if there's some natural boundary around this region. They're going to intersect where they're equal. So we have the 2x squared plus 1, or excuse me, 2x squared equals 1 plus x squared. Solve for x, and you're going to get out x equals plus or minus 1. Okay, so that gives us our two x values. So now if we look at the graphs, so you can see I made a very rough sketch here of these graphs. So going from -1 to 1, okay, we have the parabola. So this is the 2x squared down here. So that's this one. And then the 1 plus x squared is shifted up 1 unit, but it's growing half as fast as the other one. Okay, so but then they have the intersection points here at -1 and 1. So then when it comes to integrating this region, you can see my arrow right here, so indicating that vertical integration is going to be the way to go with this one, because you're going between the lower parabola and the upper parabola. Okay, so vertical integration just makes sense. So this one is going to be interpreted as a type 1 region. So the region itself, so D, we're going to have x, so it's all points x, y, so the set of all points, where x is between -1 and 1, and y goes between the lower parabola, 2x squared, and the upper parabola, 1 plus x squared. Okay, so that's our region D. So when we set up the double integral, so our double integral over D is going to be set up like this. So we get the inner integral, so this one in here. Okay, we're bounded between 2x squared and 1 plus x squared, okay, with respect to y. When we integrate the inner portion, antiderivative with respect to y is going to be xy and then plus y squared. So that's going to give us this. And then we need to evaluate between 2x squared and 1 plus x squared. So if we substitute those in, so using fundamental theorem of calculus, they're going in for the y's. So you're going to get x times 1 plus x squared plus 1 plus x squared squared. Okay, and then do the same thing for the 2x squared, and that's going to give us this one down here. Okay, so this is like big F of b minus big F of a here. Okay, so we've got those functions. We need to multiply those out, right? So multiply through, FOIL, do all that fun stuff. Combine any like terms that we have. And that's going to give us this expression down here. Okay, so we get this integral, and that is a great example of a Calc 1 integral. So just undoing the power rule. So I'm not going to take the time to go through and show you how to do that integral. If you're a little rusty on your integration, great chance to practice. Okay, because I can tell you, when you integrate this, okay, take all those antiderivatives, evaluate from -1 to 1, you end up getting 32 over 15 for that value. Okay, so just zoom back out so you can see the whole thing again. Okay, so we found the intersection points of the parabolas, Okay, we identified that it needed to be integrated vertically between the two parabolas, set up the region D, and then set up the double integrals from there. Okay, and once you have those, then it's a matter of just solving them one integral at a time. So let's look at the second example. So find the volume of the solid that lies under the paraboloid z equals x squared plus y squared and above the region D in the xy plane, bounded by the line y equals 2x and the parabola y equals x squared. So if we look at this region here, my kind of sad parabola here, and my line right here. Okay. We've got the region D. Notice that this seems to lend itself to vertical integration here. So let's go ahead and evaluate this as a type 1. Okay, so vertical integration. So if we set this up, the x values are going to go from 0 to 2. Okay, and those come again from those points of intersection between the two functions. And then the y values go from the parabola up to the line, okay, bottom function to top. So y is going between x squared and 2x. And remember, the volume is just the setup of the double integral. So by setting up the double integral, we get integrate with respect to y first between x squared and 2x. Okay. When we do that integration, so we get x squared y plus 1/3 y cubed evaluated between those bounds. And in doing that, we're going to get this result. Okay, so it's just like the last one. So you plug everything into the appropriate places, combine all your like terms, do all that multiplication, all that fun stuff, and simplify down as much as possible. You're going to get this expression. And now, again, we have basically a Calc 1 integral, so you take all the antiderivatives, evaluate it from 0 to 2, and you get 216 over 35. Okay, so you can evaluate this one as a type 1, so doing it vertically. But the interesting thing about this region is that it can be evaluated not only vertically, but it can also be evaluated horizontally. So if you look at, we have the line and the parabola, you can draw like a clean arrow from the line to the parabola horizontally, and you can also integrate that, right? So what we'll do is we'll go ahead and convert these into functions of y, right? So we had like x is h1 of y, and x is h2 of y. So the line becomes x equals 1/2 y. The parabola becomes x equals the square root of y. And our y values are going to go from 0 to 4. So our region D has y going from 0 to 4 and x going from from 1/2 y to the square root of y. Okay, that's our region D. Once we have the region D, we can set up the double integral. So that gives us the setup right here, integrating with respect to x first between 1/2 y and the square root of y, and then integrating with respect to y from 0 to 4. So I want to give you guys a chance to try one on your own, secure in the knowledge that we already know what the answer to this one is. So go ahead and pause the video here, give this one a try, see if you can work your way through this whole double integral on your own, and then we'll check in after you're done. Okay, so you should have gotten, again, the same thing. You should have gotten 216 over 35. So every problem is going to be different, of course. But when it comes to identifying the regions as type 1 or type 2, identifying them using vertical integration or horizontal integration, it can be done in some cases like we just saw. You can pick either vertical integration, horizontal integration. They're both going to give you the same thing, and you end up getting a nice clean result either way, or as clean as the result of 216 over 35 can be. But there will be cases where one is going to be preferable to the other. So it's not going to be so easy to do it one way. We might kind of be forced to do it either vertically or horizontally, depending on what that region looks like. So if we look at the next example, so evaluate the double integral of xy over d, okay, where d is the region bounded by the line y equals x minus 1, and the parabola y squared equals 2x plus 6. So this is what the region looks like. So we have the parabola here, we have the line here, and this is our region D in the middle. Now, I want you guys to see what happens if we set up the integral vertically, so as a type 1. If we do it this way, we're going to be going vertically like this. But at the beginning, notice that we're going from the parabola to the parabola here. So you would be going from bottom half of parabola to upper half of parabola, but then that stops once you reach this intersection point. Once you pass the intersection point, now you're going from line up to parabola the rest of the way here. So what we would need to do is we would need to set up two separate double integrals. So we would get the double integral from where x is going from -3 to -1, and the y values are going from the bottom half of the parabola to the top half of the parabola. That would be the first double integral. And then once you pass that first intersection point, you would be going from the line to the top half of the parabola with respect to y, and then x would be finishing off that interval from -1 to 5. So you would get this sum of double integrals, which is not necessarily impossible to calculate, it's just that it doesn't look preferable at all. So instead of looking at this vertically, what if we set this up horizontally? So we instead took the parabola and the line, and we went this direction. If we go horizontally, we are going constantly between parabola on the bottom, line on the top. Okay, so this gives us a very clean-cut relationship and a very easily integrable area. Okay, so we don't have to worry about breaking it into pieces, going between a function and itself. Instead, we can just integrate between the parabola and the line the entire way. So when we're setting up the region, we're going to have x being bounded between the parabola and the line. The y values are going to go from -2 up to 4. So we're going to get the region D here. So again, y is from -2 to 4. And the x's are going between the functions. So we have the line and the parabola. But in order to adjust them appropriately, we need to make them x equals a function of y. So like for the line, that would be x equals y plus 1. And for the parabola, we would subtract the 6, we would divide by 2, and we would get x equals 1/2 y squared minus 3. So our region D is going to be the set of all points x, y, where y goes from -2 to 4, and x goes between 1/2 y squared minus 3, so the parabola, and y plus 1. So between the parabola and the line. So when we set up our double integral, we have, with respect to x first, going from parabola to line. Once we've done that integral, y is going between -2 and 4. All right. So again, I want to give you guys an opportunity to try some of these as we're going along. So go ahead and pause the video here, give this one a try, and then when you come back, we'll compare answers, see if we got the same thing. So the answer you should have gotten is 36. Okay, so again, same kind of process as the previous ones. You're just integrating with respect to x first. Plug in the corresponding y values from the bounds here. Take that new function that is exclusively in terms of y, and then integrate that one from -2 to 4, and then you'll get a nice clean value of 36 out of that. So, for our next example, we're going to find the volume of the tetrahedron bounded by the planes x plus 2y plus z equals 2, x equals 2y, x equals 0, and z equals 0. So we need to go ahead and plot the planes for this. So you can see my diagram right here. So basically I picked a couple of the points on the axes. So on the first plane, so that was the plane x plus 2y plus z equals 2. So that's x plus 2y plus z equals 2. When x and y are 0, z is 2. So that's that point up there. When x and z are 0, we get the point 0, 1, 0. But then we don't need to worry about the x-intercept there because the other plane, so the x equals 2y plane, is going to cut it off, basically. So it's perfectly vertical, and it just basically cuts through. And these two are going to intersect in this line here. And then in the xy plane, down when z is 0, they intersect at a point. Okay, and that point we can find by setting the functions equal to each other when z is 0. That's going to give us the point 1, 1/2, 0. Okay, and again, we can solve that algebraically. So when they intersect, when z is 0, again, we get the point 1, 1/2, 0. So if we look at the region, so we've got, again, we've got the first plane here, we've got the second plane back here, but they create this region down in the xy plane, this triangular looking region down here. That's what we're integrating over. That is D. So if we look here, I've redrawn D. So this is the line, right, x equals 2y. But I went ahead and rewrote it as y equals 1/2 x, because that's the way that we typically write lines, right? Y equals mx plus b. And then we have the upper line up here, which when z is 0 is x plus 2y equals 2, also rewritten as y equals -1/2 x plus 1. Here's our point 1, 1/2 up here. Okay. And then notice that vertical integration should work just fine here. So we can go ahead and bound x from 0 up to 1. And then we can bound y between the lower line and the upper line. Okay. So when setting up our double integral, for our volume, we are integrating beneath the plane. Okay, so that's just z equals 2 minus x minus 2y. So that's what we're integrating beneath. We're integrating over the region D. And when we set up the double integral, we have x going from 0 to 1, right, just like we said, and then the y value is going from the lower line to the upper line. Okay, so from 1/2 x to negative 1/2 x plus 1. If we take the integral of this with respect to y, so we're going to get 2y minus xy minus y squared, which is what we have right here. Evaluated from lower line to upper line, it's going to give us this nice, actually pretty clean function, all things considered. That, again, that comes from just substituting in those lines into the y's, and then combining, simplifying down as much as possible. And then you get, again, this Calc 1 integral that we can then solve to get out a value of 1/3. So if we look at this one kind of as a whole here, just to reiterate the things that I was talking about. So we saw that the planes created this triangular region. We went ahead and recreated the triangular region, and we saw that we could do vertical integration on this, so we set up a vertical region, so a type 1 region, with x going from 0 to 1, y going from the lower line to the upper line, right? All the functions in terms of x. Set up the double integral, right, which again is the volume, okay, beneath this plane here. And then work our way through the double integral to get out the value of 1/3. So let's look at this next one here. Evaluate the iterated integral of sine of y squared with respect to y and then x, with y going from x to 1, x going from 0 to 1. Now, this one, it kind of sets us up to fail a little bit, the way that this is worded, because it's asking us to evaluate this integral, but notice that if we tried to evaluate this integral first, just as is, we would run into a bit of a problem. So if we evaluated this as is, we would need to integrate the integral of sine of y squared dy. And in order to do this, you would need to have some extra term. You would need to have like a y up here. You would need to have like another something else to be able to do like a u substitution, to be able to do integration by parts, something like that, that's just not there. So we can't do this one as is. Okay, so again, we cannot do this integral as is. Now, we have to be careful because this is a distinction between what we saw with the rectangular regions and with these general regions. The rectangular regions allowed us to use Fubini's theorem. Fubini's theorem said if you have a rectangular region and a continuous function, you can switch the order of the double integral, and it won't affect the answer in any way. Unfortunately, this is not a rectangular region, and if you just switch the order of these integrals, just as is, you're going to get something not only that's completely wrong, but you're going to end up with x's in your final answer because they're in the outside integral, even though you should be getting a numerical value for your answer. So we can't just switch the integrals. That's not how this works. But what we can do instead is we can go ahead and look at the region and see if we can rewrite this integral. So this is the region in question. So we had y going from x to 1. Okay, so that's y equals x to y equals 1. With x going between 0 and 1, doing the vertical integration. But that was going to give us a trouble because we couldn't integrate the sine of y squared. But we could alternatively take the same region and look at it horizontally. So instead, we have x going from the line x equals 0 up to this line. Instead of y equals x, we put x equals y, and then bound y. So y is going from 0 up to 1. And by rewriting it this way, now, so we have our new region D, where y is going from 0 to 1, and x is going from 0 to y. So you can see, as you can see, it's not a direct change here. Okay, you have to adjust it accordingly. But we get this double integral. And now the reason that this one is going to work so well is because the first integral that we're doing, this inside piece here, we're integrating with respect to x first, which means that sine of y squared, which has no x's in it anywhere, is treated like a constant. So the antiderivative of sine of y squared with respect to x is just x times sine of y squared. This gets evaluated from 0 to y, and in doing so, we end up getting y sine of y squared in the integral. And now we have this term that we're going to be able to use to do a u substitution. So we can go ahead and let u be y squared, and let du then be 2y dy. And now we have the y is covered, the y squared is covered. This is a valid substitution. In doing this u substitution, you do pick up an extra factor of 1/2 because of that 2 there. But take the antiderivative, and you get negative 1/2 cosine of y squared, evaluated from 0 to 1. Okay, and so fundamental theorem of calculus, you get negative 1/2 cosine of 1 plus 1/2 cosine of 0. Cosine of 0 is 1. You can simplify it down a little bit. I put the positive before the negative, but it's all the same thing here. Okay, so you get 1/2 times 1 minus cosine of 1. Cosine of 1, whatever that is. Don't worry about trying to approximate it using the technology. Just leave it. The exact answer is usually better anyways. So as you can see, even though we got a problem that asked us to integrate with respect to y first, we recognized that we couldn't do that. So instead of just blindly switching the integrals, which we cannot do unless it's a rectangular region with constant bounds, okay, so again, we can't do it, we instead looked at the region itself and said, is there any way that I can rewrite this region to allow me to integrate horizontally instead of vertically, right? Or using type 2 instead of type 1. Okay, so being able to convert between type 1 and type 2 integrals is a very useful tool that we have, because there are going to be some regions that, like this one, it wasn't about the region, it was about the function we're integrating under. It was about the integrand. That was the reason we were having issues. Okay, so this is one of our kind of nice ways of getting around some of these tougher functions in the integrand. And down here at the bottom of the page, we have some properties of double integrals. Basically, it's the addition property, the scalar multiple property, and the bounded property for function being bounded above by another function. These are all the same as the ones that we talked about over a rectangular region R. The only difference is they're over a general region D. Okay, so and literally that is the only difference. But it just goes to show that all of these properties will still hold even if we're dealing with a general region D. Now, if we have a region D that can be written as the union of D1 and D2. So basically D can be written as two separate pieces where D1 and D2 don't overlap. Okay, so you have something that looks kind of like this. So you have this whole region D can be divided up into two distinct pieces, D1 and D2 with no overlap. Then the integral over D can actually be split into the integral of D1, or over D1, plus the integral over D2. This is very similar to a property we had back in Calculus 1 that said if you have, right, the curve going from A to B, you can split that somewhere in the middle. The area of the first piece plus the area of the second piece equals the area of the whole thing. It's the same idea here. You can integrate over the part in D1, integrate over the part in D2, add them together, and that gives you the value over the whole region. Okay, so very similar to one of our Calculus 1 properties. Now, when is this property useful? Well, it's particularly useful in regions that look like this. Something like this region cannot be integrated vertically or horizontally as is. So think about what if we tried this vertically. So we're going along, so we're integrating vertically, everything's all good, but then all of a sudden, whoops, it ends up getting split into two separate pieces because the function kind of comes back on itself there. So that wouldn't really work for vertical integration. And then what if we tried horizontal integration? So, we're going along fine, doing our horizontal integration, but then again, whoops, it ends up getting split, right? Cut off by itself. So then you have to set up multiple integrals to do all of this. So we can't use just vertical or just horizontal integration. What we can do instead, split that region, so I tried to approximate it as best as I could, split that region into two separate distinct regions, so D1 and D2. D1 can be integrated vertically, right? Everywhere here we're going from bottom to top. D2 can be integrated horizontally. Everywhere here we're going from left function to right function. So we can, instead of taking the integral over the whole region D, we can just take the integral over D1 plus the double integral over D2. And this one would be done vertically, and this one would be done horizontally. Okay. So we can use this property to kind of get around regions that are harder to integrate otherwise. Now here's an interesting property. If you integrate the constant function f of x, y equals 1, so if you integrate the function 1 over some region D, we actually get the area of the region D. Now this is kind of interesting because up until this point we've been looking at volumes, right? We're finding volume under a surface above the region, but it turns out if the surface is just the function 1, the volume of the solid is equal to the area of the region D. Now this is interesting because the area of the region D, that's what Calculus 1 and Calculus 2 are about, right? Finding the area of a region under a curve, right? Or between two curves. But it turns out we can also apply double integrals to this as well. So say we have some general region defined by z. Okay, so z equals 1. So this has a constant height of 1 here. Right, so again, that height is 1. We get the region down here. Okay, so that's D down here. We can define the volume of this solid. Okay, so the volume in here is defined as the double integral over D of 1 dA, because again 1 is the function that we're integrating beneath. So this is how we define volume, but the volume in this case, where you have a height of 1, is also going to be the same thing as the area of the base times the height. So that's going to be area of D times 1, which of course anything times 1 is just itself. So we get volume, we know is the double integral, but volume is also equal to the area. So we can conclude that the double integral over d of 1 dA is equal to just the area of d. Okay. So this is kind of interesting that now we're using Calc 3 properties and double integrals. You can use them to find solutions to Calc 1 problems. And the verification of this, like the pattern that these problems take, you'll see very quickly why this works. It ends up giving you like a perfect example of finding area between two curves if you were to try this. And so we'll see that as we go through examples in future sections as well. But really interesting property where we're getting a volume equal to an area, so we can find area of a 2D shape. And then we have one last property here. So we talked about the idea of functions bounding each other, but what if we have a function that is bounded above and below by two constant values? Okay. What if a function is bounded above and below by two constant values? Well then, it turns out, the double integral, that volume, is going to be bounded above and below by those constants times the area. And this goes back to that same exact property that we were just talking about. Basically, it's saying, I have kind of a quick little diagram down here. Basically, it's saying if you have some region in here, it's bounded above by a constant value, big M. It's bounded below by a constant value, little m. The volume beneath the solid here, okay, so whatever volume that is going to be smaller than the volume under the big one. Okay, so it's smaller than this whole volume here, right, which is big M times the area. But it's bigger than the volume under here, which is little m times the area. Okay, so that's basically what this property is saying. It's if the function is bounded above and below by two constants, we can bound the area or the volume as well using this same calculation. So using basically the area of the base times the height, whether that be little m or big M. So, and that brings us to the end of section 15.2. This is our introduction into double integrals over a general region. When we come into the future sections, we're going to be looking more at different types of double integrals, how we can calculate different types of regions, all of that good stuff. So that brings us to the end of this section.